So today we're looking at the question minimum operations to make median of array equal to k. This was featured in weekly contest 329. So the question reads, we're given integer array nums and a non-negative integer k. So we have nums and k as our inputs. In one operation, we can either increase or decrease any element by 1. We want to return the minimum number of operations needed to make the median of nums equal to k. However, we have a unique definition of median in this case. The median of an array is defined as the middle element of the array when it's sorted in non-decreasing order. And if there are two, which is the case when the length of our array is even, we want to take the larger of those two values. So you can see here, this is one example we're given, 2, 5, 6, 8, 5. So to find the median, we need to sort this, and we get 2, 5, 5, 6, 8. And here our median would be 5. And then we can get this because the length of our array is 5 divided by 2 equals 2. So what we have to do is make this 5 equal to our k value here. So you might be thinking, why don't we just take this, we'll decrement this by 1, and our array becomes 2, 5, 4, 6, 8, right? So we see that our median is 4, and we're done. Well, actually we're not, because the median definition is that it has to be the middle element of a non-decreasing array. As you can see, by making this element 4, we actually violated that, and we saw that 5 comes before 4, so this is no longer non-decreasing. So you could say maybe we sort it again, so we'll have 2, 4, 5, 6, 8. Again, our median is 5, which is not 4, so we then decrease this to 4. And now we'll see that our median is actually 4, and this is in sorted order. Let's look at another example. The same array, but where our value is higher than our median, our k value. So 2, 5, 6, 8, 5, and our k equals 7. So again, if we sort this, 2, 5, 5, 6, 8, we'll see our median is 5, and we need to make this 7. Right, so then we can increment this to 7, and our array becomes 2, 5, 6, 7, 8. Again, our median now becomes 6, so we can increment this 2, 5, 7, 7, 8. Right, so basically we now see that our median is 7 and our array is sorted. So you might be thinking, we're resorting the array every single time, which is an n of log n operation. And potentially, if we have to update every new median, we'd have to do that n times, which is an n squared of log n operation. This is going to be way too slow, and we can't do this. So if we look at the final result array that we get, and kind of look at what elements have changed. So you'll see when we originally sorted our array, it became 2, 5, 5, 6, 8. Then we take this and make it a 7, right? So what about this array is not sorted? Well, we see that if we go forward from 7, right, we see a 6 here. So we can immediately tell that this is not sorted because the next value is smaller than we just made the median. And you can see in this previous example, the next value that we actually updated was 6. So in this case, we can just go ahead and make 6 equal to our median as well. And you might be able to see a pattern here. Essentially what we're doing is looking at two cases. So in this case, if our k value is higher than the starting median, which is in this case here, we set our middle value to the median, and then we want to go forward through the array, the sorted array, and see any value less than what we want the median to be, we would just update that. Similarly, if we had a smaller value, we do the same thing, right? So if k was 4 here, we would set this to our median, and now we say potentially anything less than this value might cause this array to not be sorted, right? So then we'd go back and say, do we see anything greater than k? If we do, we update that as well. So essentially what we're doing is two distinct cases. Either when we have k greater than the original median, we'll update it and then move forward, checking any elements less than that desired median. If we have our original median greater than the median that we want, we'll decrease that value to our median and then go backwards, looking for any values that are greater than the median that we want, right? And basically what we do is just count the differences between these numbers. And we do have to sort this, so this is n of log n, but thankfully we're just going through the array one time, so our time complexity is capped here. And we're using no space complexity, we're just sorting the array in place. So one case we didn't think about is the case where we have an even length array, right? And that might slightly change how we view our median. So usually when we have an even length list of numbers, to get the median, we would take these two numbers and we would get an average of them. So in this case, that would be 7 divided by 2 would equal 3 overall, right? But however, remember, this question gave us a unique definition of what median is. It said if there are two numbers, we always take the maximum, right? So in this case, we have 3 and 4, and we take 4. But think about it. If this array is sorted, would there ever be a case where we take this value 1 before the middle? Well, no, because this value in a sorted array will always be equal to the second value, if not less, right? So we can basically make the assumption that if we do have two values, the second one we can always use because it will always be at least greater than or equal to the first one. What that means is that in the case of either an odd length array or an even length array, we can always use n divided by 2 as that index and not worry about any of the logic of being less than or greater than. So let's hop over into the code and I can show you exactly how that works. So the first thing we want to do is sort this input array, and this allows us to find the median right in the middle of this set of numbers. Then we'll calculate our midpoint, which is just the length of nums divided by 2, and then instantiate this variable changes, which will just keep track of how many changes we've had to make to satisfy this median condition and what we will eventually return at the end of this function. So the first case is if our middle value is greater than the desired median. So what we'll then do is we'll record the difference between that desired median and this value, and then set our median equal to that k value that we want. Then we'll start looking through the left side of that median. And while there are elements left and that index is greater than the desired median, we'll record the changes and then we will decrement our index by 1. On the other hand, if that value is less than the desired median, we still record the changes and we still update that middle value. However, in this case, we're going to look through the right side of the array. So basically, while the index is less than the length of nums, and while the value at that index is less than our median value, we're going to record those changes and increment. So we're just handling the two distinct changes where it's less than and also greater than. Then at the end, we're going to return our changes, and let's submit this and make sure it works. And it does. Hopefully this was helpful and it made sense. Thank you very much. Thank you for watching.